now we are going to start module 2 of chapter 6. This module is devoted to the solution of one-dimensional wave equation. We have chosen one-dimensional wave equation because it is easy to handle, and for some physical situation it is sufficient to consider the problem as one-dimensional problem. We shall solve one-dimensional wave equation using 4 different methods. Firstly, we shall solve it using canonical transformation. In the second method, we shall find the D'Alembert solution of wave equation. Then we shall solve this equation using Riemann-Volterra method, and lastly we shall use the method of separation of variables to find the solution of one-dimensional equation. First, we shall use canonical transformation to find the solution. For derivation, now we are going to slide presentation. The one-dimensional wave equation is given by del 2u del t square equals to c square del 2u del x square, where c is the wave speed. First of all, we shall solve this one-dimensional wave equation using canonical transformation. From the equation which is written in 1, it is easy to find that the characteristic lines are xi equals to x plus ct and eta equals to x minus ct. Now, we shall try to write the given equation in terms of u, xi and eta. So, for that purpose, we calculate del u del x, which is shown here. It becomes del del xi plus del del eta of u, or equivalently we can say that the operator del del x is equivalent to del del xi plus del del eta, and the operator del del t is equivalent to del del xi minus del del eta. So, if you substitute this, so in this example we are trying to write the equation, we are trying to transform the equation from x t to xi eta. So, in terms of xi eta, the equation becomes del 2u del xi del eta equals to 0, and it is easy to find solution of this equation. The general solution of this equation is u equals to phi xi plus psi eta, where phi and psi are arbitrary functions of xi and eta respectively. Now, in terms of x and t, the solution is u equals to phi x plus ct plus psi x minus ct. The two terms in equation 2, they are interpreted as the waves travelling in two directions. One is to the right and another one is to the left. Now, if we multiply the argument by k, that means u equals to phi k times x plus ct plus psi into k times x minus ct is also a solution of the one-dimensional wave equation, where k is an arbitrary constant. Now, if we assume w as k into c, then the solution can be written in the form u equals to phi kx plus omega t plus psi kx minus omega t. The term kx plus minus omega t is called the phase of the travelling wave, and the term x plus minus ct are known as characteristics of the one-dimensional wave equation. In chapter 4, we have seen that Cauchy type initial value problem is overdetermined to find solution of a Laplace equation. But in case of wave equation, Cauchy type initial value problem gives an unique solution, and that solution is called D'Alembert's solution. Now in our next slide, we are going to discuss about the D'Alembert solution of one-dimensional wave equation. Suppose we have the Cauchy type initial value problem, which is written by equation 4 and 5. Equation 4 is nothing but one-dimensional wave equation, and equation 5 is the initial condition, which says that u at x0 equals to eta x and del t of u at x0 equals to nu x. We have seen in the last section that solution of equation 4 can be written as u x t equals to phi x plus ct plus psi x minus ct, where phi and psi are arbitrary function. Now we have to solve the equation 4 together with the initial condition 5. Since phi and psi are arbitrary, now we are using the initial condition. The first initial condition says that u x0 equals to eta x. So if we substitute that in the solution, where u equals to phi plus psi, so in this equation we put t equals to 0. So that gives phi x plus psi x equals to eta x, and the second initial condition del u del t equals to nu x at t equals to 0 gives the another equation c into phi dash x minus psi dash x equals to nu x, and this equation can be solved to get the solution which is written in equation number 7. So solving that, we get phi x minus psi x equals to 1 by c integration over 0 to x nu xi d xi. Now solving the equation phi plus psi equals to eta and phi minus psi equals to 1 by c integration 0 to x nu xi d xi, we obtain the expression for phi as phi equals to half eta plus 1 by 2c integration 0 to x nu xi d xi, and psi equals to half eta x minus 1 by 2c integration 0 to x nu xi d xi. Therefore, solution which is u, which is equals to phi plus psi, phi it becomes half eta x plus ct plus 1 by 2c integration 0 to x plus ct nu xi d xi plus half eta x minus ct minus 1 by 2c integration 0 to x minus ct nu xi d xi. So it can be written after simplification as u equals to half eta x plus ct plus eta x minus ct plus 1 by 2c integration x minus ct to x plus ct nu xi d xi. The solution which is written in equation number 9 is known as D'Alembert's solution of the one-dimensional wave equation. In chapter 3, we have already discussed the Riemann's method or Green's function method to find solution of a partial differential equation. There I mentioned that this method is very important to find solution of a one-dimensional wave equation. Now I am going to present how this method can be used to find solution of one dimensional wave equation through slideshow. Now, in wave equation, we first give a transformation y is equal to Ct, and the equation reduces to the form del 2u del x square equals to del 2u del y square. Suppose we have the condition u is equal to eta xy and del u del n equals to nu xy on C. That means the value of the variable u and the normal derivative of u are prescribed on some curve C, and let gamma is the projection of C on xy plane. Suppose we are to find the value of u at some point x bar y bar of the wave function u at the point P, and the characteristics of the equation taken through the point P are given by x plus y is equal to x bar plus y bar, x minus y equals to x bar minus y bar. The figure is shown here. So, we are interested to find the value of u at the point P having coordinates x bar y bar, and the two characteristics are PA and PB, and the value of u are prescribed in the curve C. The C is shown here. So, let us first assume that the first characteristic, that means x plus y is equal to x bar plus y bar, intersects the curve C at point A, while the second line intersects it at the point B, which you can see in this figure. This is the first line, it intersects the curve C at the point A, and this is the second line, this intersects the curve C at the point B. Now, think about the operator L, which is del 2 del x square minus del 2 del y square. So, here we have to find the solution of LU equals to 0, and you can easily verify that this operator capital L is self adjoint. Now, we calculate this double integral over sigma WLU minus ULW is, this is the expression for LU and this is the expression for LW, and after some calculation it is equals to this expression which is written in the last line, and this can be again written in this form del del x of w del u del x minus u del w del x plus del del y of minus w del u del y plus u del w del y dx dy, and this is equals to, this is the double integral or the surface integral. Now, this surface integral is equals to the line integral, which is written here integration over c dash u cos nx plus v cos ny ds over c dash, where c dash is a closed path A P B A enclosing the area sigma. So, if we go back to the figure, so c dash is the line which enclose the area sigma, and sigma area is the area which is bounded by PA, BA and AP. So, the expression for capital U becomes W del U del x minus U del W del x, and V equals to minus W del U del y plus U del W del y. Now, the Green's function w must satisfy some conditions which are written here. The w must satisfy LW equals to 0 and del W del n equals to 0 on AP and BP. These are the two characteristics, and W equals to 1 at the point P. Now, to satisfy these three conditions, the obvious choice or the easy choice for W is W equals to 1. So, if W equals to 1, it will satisfy all these three conditions, and we have also LU equals to 0, and then if we go back to the relation 13, the left hand side of that expression is WLU minus ULW. So, if you choose W equals to 1, LW is 0, and we also have LU equals to 0. Therefore, left hand side becomes 0. So, 0 is equals to the right hand side, this part U cos nx plus V cos ny ds. So, it becomes, this is the parts of C dash. C dash is the part AP, PB plus BA, and this is del U del x cos nx. From here we got the expression. If you observe the expression for capital U, we have chosen W as 1. So, for that this term becomes 0, del W del x. So, capital U becomes del U del x and capital V becomes minus del U del y, because W being 1, this part gives 0. So, substituting this, the expression for U and W in equation 13, it becomes del U del x cos nx plus minus del U del y cos ny ds. So, it is written here. So, it is written in equation number 15. Now, we have to integrate over AP, PV and PA. This is a closed curve. Now, along PA, that means this is the characteristics x plus y is equal to x bar plus y bar. So, for that, for this characteristic, the normal, this is the angle between the normal to the characteristic with the x axis. So, for that cos of nx becomes 1 by root 2, cos of ny becomes 1 by root 2, and subsequently the value of ds is minus root 2 dx, and this is equals to minus root 2 dy. So, substituting all these, we get integration over AP del U del x cos nx minus del U del y cos ny ds equals to minus integration a to p del U del x dx plus del U del y dy. So, this is nothing but dp. So, after integration this term gives UA minus UP. Similarly, on the characteristic PV, which has equation x minus y equals to x bar minus y bar, we obtain the expression, the value of the integral along PB as UB minus UP. Now, substituting the values of this integral in this equation, equation number 15, it reduces to the form U at P equals to half of UA plus UB minus half integration over AB del U del x cos nx minus del U del y cos ny ds. and this solution is the solution of Cauchy problem of one dimensional wave equation, and we obtained this solution using Riemann's method. In particular, if the value of u and del u del n are prescribed on the axis y is equal to 0, then we can show that this solution 16 reduces to the D'Alembert solution. The derivation can be seen from the e-text of this module. We have already used the method of separation of variable to find solution of different types of equation. This method is very strong because it can be used in a wide range of differential equation. Now, we are going to use that method to find solution of one dimensional wave equation in Cartesian coordinate system, plane polar coordinate system and spherical polar coordinate system. Now, we are going to our slide show. We have one dimensional wave equation and we are trying to find solution of that equation using separation of variables method. For that purpose, we write the solution u as product of two functions capital X and tau, where x and tau are functions of small x and small t respectively. Now, substituting the expression for u from here to the wave equation, we obtain the equation which is written in equation number 17. Now, we separate the function capital X and capital tau in this way, and we assume that small k as our separation constant. In the first case, we assume our separation constant as some positive constant. So, we assume k is equal to mu square, where mu is a real number. So, substituting that, we obtain two separate equations for capital X and tau, and it is easy to solve both the equation, and the solutions are given here. Capital X is C1 cos hyperbolic mu x plus C2 sin hyperbolic mu x, and tau is also linear combination of cos function and sin function, hyperbolic functions. Thus, the solution u can be written as these are the product of capital X and tau. Now, in the second case, we assume our separation constant as 0, then the equations for capital X and tau becomes del 2x del x square equals to 0, del 2 tau del t square equals to 0, and the solutions of these equations are capital X is C5 x plus C6 and tau equals to C7 t plus C8, where C5, C6, C7, C8 are constants. So, the solution can be written as u is equal to this product of capital X and capital tau, which is written in equation number 19. Now, in the last case, we assume the separation constant k as some negative number. So, we assume k as minus mu square, and the solution become u equals to some C9 cos mu x plus C10 sin mu x into C11 cos C mu t plus C12 sin C mu t, which is written in equation number 20. Now, I am going to discuss the solution in plane polar coordinates. The equation, wave equation in plane polar coordinate takes the form which is written in equation number 21. Now, in this equation, we assume time periodic solution. So, for that purpose, we write the solution in the form u is equal to capital R into e to the power I omega t. So, substituting this expression for u in the equation 21, we obtain the equation for capital R as d2r dr square plus 1 by r dr plus omega square by c square r equals to 0. And you can notice that this is famous Bessel equation, and the solution of this equation is the linear combination of two Bessel function of order 0. So, r equals to a j0 omega r by c plus b y0 omega r by c, where j0, y0 are Bessel's functions of order 0 and of first kind and second kind respectively. Now, the solution can be written in complex form also in this way. So, r can be written as C1 J0 omega r by c plus I y0 omega r by c plus C2 into J0 omega r by c minus I y0 omega r by c. Now, this quantity in the bracket, this is known as Hankel's function. So, capital R can be written as C1 H01 omega r by c plus C2 H02 omega r by c, where H01, H02 are the Hankel functions of first and second kind of order 0, and they are defined in this way, which is written here. Therefore, in terms of Hankel function, the solution can be written as u is equal to C1 H01 plus C2 H02 into e to the power I omega t. Now, I am going to discuss the spherical polar coordinate system case, where the equation, wave equation, can be written in the form which is given in equation number 23. Again, we are applying separation of variable method, and we are assuming the periodic solution. So, for that purpose, we are writing u as some function capital R into e to the power I omega t. So, if you substitute this in 23, the R equation becomes this d2r dr square plus 2 by r dr plus omega square by c square r equals to 0. This is not Bessel equation, but if we give some transformation, this equation can be reduced to Bessel equation. So, for that purpose, we give a transformation which is shown here. Capital R is equal to omega r by c to the power minus half into capital F. So, the equation in terms of capital F becomes this. So, this is Bessel equation of order half. Therefore, its solution is the linear combination of j half and j minus half, which is shown here. So, capital F is a dashed j half omega r by c plus b dashed j minus half omega r by c, where j is the Bessel function of order half. Now, in terms of capital R, or the value of capital R can be written as capital R is 1 by square root smaller into a j half omega r by c plus b j minus half omega r by c, where the constant a and the constant b are defined as a is equal to square root c by omega a dashed and b is equal to square root c by omega b dashed. Now, you can note that the value of j half can be written in terms of sine function as j half equals to square root 2 by pi x sin x and j minus half x is square root 2 by pi x into cos x. So, capital R becomes square root 2c by pi omega into 1 by r a sin omega r by c plus b cos omega r by c. And the solution also can be written in complex form in this way. Capital R equals to 1 by r c1 e to the power I omega r by c plus c2 e to the power minus I omega r by c. So, in complex form the expression for u can be written as 1 by r c1 e to the power I omega by c into r plus ct plus c2 e to the power minus I omega by c r minus ct. So, this is the solution of wave equation in spherical polar coordinate system. Therefore, in module 2 of chapter 6, we obtained solution of one dimensional wave equation using different methods. We find D'Alembert solution, Riemann solution and the solution using separation of variables method. It is to be mentioned that the solution obtained by all the methods is unique. If we start from same initial condition, the uniqueness of solution can be seen in our e-text. Thus, we end module 2 of chapter 6.